welcome everyone to the season finale of the ZX seminar. And I'm happy to introduce Yichen Xu and Arpit to present fault-tolerant protocols through spacetime concatenation. So take it away.
Okay, so hi everyone, I'm Yichen, and today I'm going to be talking about this recent work that we've been doing called fault-tolerant protocols through spacetime concatenation. So since it's a two-people work, we are going to share the workload. So I will cover, the first half of the talk, and Arpit will cover the second part. And since it's a very long paper, and it's very unfortunate, we made it so long. So this talk is probably just covering some basics of our thoughts. And yeah, if you guys are interested, I highly recommend you guys read the paper. And if you guys have any questions throughout the talk, you guys can stop us at any time. And also, if you guys have any questions regarding our paper, feel free to email either of us, and we'll happy to answer any of your questions. So yeah, it's quite challenging for me to talk to an audience that's very familiar with ZX calculus. So I'm not starting with ZX calculus, but just do a very basic kind of review of quantum error correction, since this talk is about fault-tolerant protocols. So what we mean by a quantum code is basically we have some quantum state side that we want to protect against all sorts of defect and noises in realistic quantum devices. So what we do is we encode the quantum state into a larger Hilbert space, so that the code space is basically a subspace of the enlarged Hilbert space. And throughout this talk, when we mean a code, we usually mean a Pauli stabilizer code, which means that the standard notation for a Pauli stabilizer code is denoted by these three numbers, n, k, and d. N is the number of physical qubits of the code, k is the number of logical qubits, and d is the code distance. And the code can usually be specified by a group of Pauli operators that form a group we call S, which contains n minus k elements. And the logical space is simply the Pauli group of the n physical qubits quotient the stabilizer group. And we are also focusing on very specific, class of stabilizer code in this talk, which is, quantum LDPC codes that are defined on qubits with some sense of locality. It's either, geometric locality or some graph sense of locality. So, we have a local basis to work with. And what we mean by a fault-tolerant protocol that we are aiming to construct is basically a dynamics, a space-time dynamics, aka a circuit that prepares a logical state in the code space, and also preserves the logical information while the state actually evolves over time. And on top of that, we the logical space can evolve, and we can do some meaningful computation in this logical space along the way, whilst being protected against error. So these are the terminologies we're going to use in the talk. So we're going to see just an example of a very simple quantum error correction code, which is the 422 code. So the 422 code, as the name suggests, is a code of 4 qubits, 2 logicals, and the code distance is 2. So the stabilizer group is very simple. It's basically a product of all 4 x's and the product of 4 z's on the 4 qubits. So in order to actually implement the code, we not only need to specify the stabilizer group, we actually need to find a way to repeatedly measure the stabilizers. So there are different ways, historical ways that people can perform these measurements. So there are 3 examples that I show on the slide. There is this single ancilla way, which is widely used in experiments nowadays. So what you do is you introduce an ancilla. For example, if you want to measure the product of 4 x's, right? If you want to measure the product of 4 x's, you introduce an ancilla, which is initializing plus. And then you do a series of C-naughts between the ancilla and the 4 physical qubits inside the code. And finally, what you do is you perform a projective measurement on the ancilla and read off the value of the stabilizer. This is, we call it the single ancilla syndrome extraction circuit in our paper. But the original proposal is proposed, in this paper by DiVincenzo and Shor in 1996. And there are other ways. For example, this Shor's style syndrome extraction is to prepare a cat state or GHD state that's of the same size of the stabilizer you want to measure. So for example, if you want to measure a product of four x's, you prepare a cat state of length 4, and then do a C naught between the codes, between the physical qubits in the code and the qubits at the cat state. And then you measure the entire cat state. And based on these measurement outcomes, you can infer the value of the product of four x's. And there is also the so-called neo way, in which you prepare another code state, but initialize deterministically in the code space 0 and 0, and then you do this so-called transversal C naught between these two pieces of codes, these two blocks of codes, and then you do a projective measurement, a transversal measurement of the code state, the extra code state you preserved, and read off the values of measurement, and then you can infer the value of the stabilizers. So so these are the historical ways of doing singular refraction. There are also other ways of doing singular refractions. But in general, what we expect is that the circuit of us operating the code looks like this. So this is on the right. There are a lot of terminologies on this slide, so bear with me. So what we just did is that the protocol on the right, like if time goes from the bottom to the top, then what happens is we essentially have a circuit where we have something going on in the box, which is marked by the yellowish color here. So we do something. So before and after, we essentially are inside a stabilizer group, right? The physical qubits of the circuit will be measured in their the stabilizers of these physical qubits will be measured. So what happens is the physical qubits will always be in this code subspace, without error occurring. So that the stabilizer group, the instant stabilizer group, is kind of the same when time evolves. But there could also be another more general case where the stabilizer group is actually evolving over time. And actually, if we look closely to what just happened, is that there isn't really a time, that there was a time where after all your measurements, the code obviously stay in the code space, but along the way of this circuit, actually the stabilizers themselves are evolving, right? They're evolving because you introduce ancillas and you do some unitary gates. So the stabilizer group actually is constantly evolving, although we just assume that this is something inside somewhat the black box. So if you really look closely, what happens is in a general fault tolerant circuit, the stabilizer are actually always evolving over time. And so what happens in general is basically the picture on the left, which is there you have a instant stabilizer group that's dynamically generated and constantly evolving, right? So what happens is we're aiming for such a protocol that can naturally incorporate the case where the stabilizer group is constantly evolving, and that's what we're aiming to construct. So the tool, as everybody knows, when you guys the tools that we're using to construct the dynamical code is the ZX calculus. And since I think the audience is pretty familiar with ZX calculus, we assume. So this is just our convention. This is a little bit different from the red and green colors. We just use the white and black node. So the white node is the X tensor, the X spider, and the black node is a Z tensor. And yeah, that's the convention that we're using for ZX calculus. So if you use ZX calculus and start rethinking about all these circuits that operates on the 422 code, what we find is that you can convince yourself, it's a very straightforward exercise in ZX calculus, that you can basically represent all these circuits in ZX calculus and you do a bunch of ZX equivalent. You apply a bunch of ZX rules, and what you find is that all of these protocols are essentially equivalent to the following ZX diagram. So this ZX diagram has one Z spider in the center, and 4X spiders on 4 physical qubits. And this is basically the way that the product of 4X's is measured. So this is rather simple, right? This is, that's the power of ZX calculus. It reveals, the actual functions of the circuit. So On top of that, people realize that, that the notion of fault tolerance is actually well, captured in ZX calculus too, because, when we do the syndrome extraction circuit repeatedly, what happens is the following, right? So this essentially, the first spider here is a measurement of product of four x's. The second spider here is a measurement of four z's, and so on and so on, right? So, but when you repeat the circuit, what happens is, it creates the so-called spacetime detectors. So the spacetime detectors are essentially, the polywebs on, the polywebs on the ZX diagram that's closed in space and time. So for example, in the case of 422 code, what happens is, we can draw these, space-time detectors on this, I don't know if let's try this. Yeah, so for example, if you focus on spider here, what happens is, this Z spider is stabilized by this polyweb that I'm marking in red, like these are all x's, right? And it can go ahead in time and it reaches Z spider. What happens is, it goes into it. Sorry, look a little bit messy, but it will close at the next projected measurement x. So what happens is, it forms a closed polyweb in space and time. So what happens is, whenever there's an error, for example, a phase error Z happens anywhere on this space-time detector, for example, if it happens here, there's a phase flip error at this space-time location, then, what happens is it will anti-commute with the polyweb of, X stabilizers. So it will trigger its value, right? Meaning that, you have a lot of measurements along the way, right? There are different ways you can interpret this ZX diagram, but no matter how you interpret it, there are multiple measurements. And what happens is all of these measurements will multiply to -1 instead of +1 if there's a phase error occur along the way. And similarly, you can visualize, the Z stabilizer and the Z space-time detector on this ZX diagram. And so there's a very famous paper now, like this paper by Baum and Latinsky and collaborators. And I think that the paper basically, captures all of these insights of why, fault tolerance can be directly visualized on ZX calculus. So with the intuition of that, people thought, okay, so since, all these, previous syndrome extraction circuit are essentially this ZX diagram, so if we try to, employ, ZX rules and try to rewrite this exact diagram, we are basically, always getting a syndrome extraction circuit. And we can demand, for example, some nice properties of the syndrome extraction circuit. And then we can, basically play with ZX rules and get the desired circuit that we want. So one major line of work that I want to share is, oops. I think this. Sorry. Yeah, so one major line of work that I want to share is, these two works that I think both occurred at the ZX seminar before. So what these works did is essentially, just that. They're trying to rewrite the exact circuit that's shown in the previous slide. And the aim of these rewrites is, to bring the syndrome extraction circuit to something that looks that is, carried out by pairwise measurement of either X or Z, right? For example, this Fault-Tolerant paper last year did exactly that. Along the way, they justify that, such a procedure will preserve the code distance if you, employ the circuit to do syndrome extraction. And similarly, there's another work which called dynamical weight reduction, and the philosophy is also, try to introduce a bunch of ancillas as little as possible in order to convert the syndrome extraction circuit into pairwise measurements. So, but along this lines, actually, the pairwise measurements as a way to extract syndromes is not a new thing, right? Actually, there are a lot of works that exist even before the ZX age where, these powerful tools can be used to rewrite circuits. And for that, I want to highlight, a series of works starting from Haah and Haah, and followed by all of these papers. And sorry if I missed out something, some papers here. But all these works are before ZXH. They don't, they're actually not operating on the syndrome extraction circuit directly. What they did is they have a strong physical intuition of how how, for example, anyons are condensed in topological codes, and through these intuitions, they're able to construct codes based on these intuitions, and these dynamical, Fouquet codes can actually perform something that's the previous works that failed to achieve, which is they can realize possible non-trivial logical automorphisms, and these logical automorphisms are basically are basically from the anyonic intuitions as well. So, but a huge limitation of these works is that they rely heavily on the topological nature of the code. By that I mean the excitations on or the syndromes of these codes are topological. They are anyons of a topological order. So there are a lot of intuition that you can use from there. But for a general quantum LDPC code, maybe you don't have that strong sense of what the physics actually is, right? What are the anyons? Like, how do they braid? We don't necessarily know. So there seems to be a lack of a general construction of these interesting Fouquet codes that can perform in non-trivial logical automorphisms. So we sort of bring these two ideas together and start thinking, okay, what is the general structure of the syndrome diffraction circuit? So our logic goes like this, right? So suppose we want to generalize this notion, right? But we don't directly jump in like I give you a 422 code, you will give me the thing in the dotted box, right? But we say, okay, maybe we take a step back, right? We shouldn't rush into thinking, okay, this is automatically response, right? What is the most general form of syndrome extraction circuit? So that brings us to the second diagram on the right that we're trying to operate, which is it's a ZX diagram, right? It's inside a box, and we just want it to perform certain functions, right? The functions that if you have a product of four x's is mapped to a number, right? It's mapped to a number so that the product of four x's is measured, plus the product for z is measured as well by the CX diagram. And nevertheless, it generates a new stabilizer, which is a product of four x's, a product of four z's. So it measures, incoming stabilizers of your code, and it generates, another set of stabilizers on the outgoing side of the black box, right? And along the way, the logical operators, because we haven't specified what they do, right? But we have to make sure that, they go through this box, right? The logical information is preserved by this circuit. So that leaves us actually a freedom to specify what logical automorphism that this black box can perform. So in total, this is kind of a general picture of a syndrome diffraction circuit. And what we're trying to do is basically say, okay, how do we construct the CX diagram, right? Based on these information that we want, right? So that is basically, we were trying to utilize, a sense of locality of the incoming and outgoing stabilizer codes to bring them into, local pieces, that these tiny gadgets of small ZX diagrams that are interconnected between these. So sorry, these small ZX diagrams are interconnected, and they form, the circuit of syndrome extraction. So in general, this is kind of the picture that we present in our paper. So a reminder that the time now goes from bottom to up. So what happens is, this is our kind of giant black box that we demand to have, these three functions, right? It measures the incoming stabilizers, it generates a set of outgoing stabilizers, and it preserves logical information along the way. So if you want to decompose this ZX diagram locally, right? So we can imagine them being a set of local gadgets that lives just at the spatial location of the physical qubits of the stabilizer codes, right? And they're interconnected, and the connectivity between these gadgets can be inferred from the tanographs of the stabilizer codes. and we have an algorithm in our paper that makes sure that if you connect these gadgets correctly, they will always function. Correctly to measure and generate these stabilizers. And if you trace the poly web of the stabilizers evolving over time, what happens is for example, for a incoming stabilizer S marked in red here, what happens is it's supported on a bunch of physical qubits, right? The physical qubits before entering the dynamical codes are the ones that are pointing downwards, right? So it enters the black box on these legs, and it enters the gadget, right? And because the operator S is measured, so that means the S must be the polyweb of S must stay inside this black box, right? So that means it kind of needs to stay on the bonds, right, between that connects all these gadgets, right? So this is just a sketch of what this can be achieved, right? For example, if this a few body stabilizer S is mapped to these bonds and they're interconnected, that means okay, yeah, sure, the S operator is measured. And similarly, if you want to generate a new stabilizer, you have to make sure that there's nothing supported on the incoming legs. They only support on outgoing legs and the internal legs on the bonds, right? And simultaneously, if you want to preserve the logical information, you can trace the polyweb of a logical operator. And so the logical operator needs to go through this entire black box, right? It cannot stuck inside the black box. Otherwise, logical will be measured. So logical is not measured, logical is preserved. So it has to go through the black box, but it can leave some trace, right? It can leave some bond operators on the bonds that connect the logical operators, but that's fine. So this is the general structure of our construction. And because you realize that, oh, if you just zoom in, sorry, the question?
Yeah, is do I understand correctly that the wire that goes on top right like loops back around to the bottom left?
Loops?
I don't know. In the previous slide, you had some loops going around, so I was just wondering if they're.
Oh, yeah, I see. So this is because the 422 code is like defined on the, you can say on a loop. On a loop, like the four qubits form a loop. So that's why that's why I if you use the connectivity correctly, it also the gadgets will form a loop. So, but the connectivity in general, like you can infer it from the connectivity of the qubits, like how they participating in the stabilizers, right? So based on how they participate in different stabilizers, which is described as tiny graph, you can draw these connections between the gadgets using an algorithm we had, and it will guarantee that it works.
Okay, thank you.
Yeah. So any other questions? Okay, so the key observation kind of we had on this picture is that if you zoom in locally, what you see is that this gadget actually is a local encoder. What we mean is that it encodes poly operators on the incoming and outgoing legs to a set of bond operators, right, on the internal legs that connects these gadgets, right? So this actually means that this circuit that we're constructing is nothing but a interconnected series of encoders, right? So it actually resembles some previous works which people call the quantum Lego codes. But in quantum Lego codes, what people are trying to do is they are trying to concatenate, or they're trying to connect small local encoders to become a bigger to become a bigger encoders, right? But what we are doing here is we are not doing an encoder. What we're actually doing is we're doing a syndrome extraction circuit, right? So we are not only specifying what code we are operating on, we're also specifying what dynamics they're actually going through, right? How this code is implemented. So that's the major difference of us and the quantum Lego codes that occurred a few years ago. Okay, so how this is actually achieved, right? So suppose we already know how these bond operators are, right? Which you actually need to specify them based on the stabilizers in the stabilizer codes. But suppose you know what local encoder that you already had based on the algorithm. So the first step you need to do is actually need to deploy a ZX diagrammatic algorithm to actually write what's inside the gadget, right? So this is a work that also has occurred at ZX Seminar by Andre Kessing and collaborators. So you first draw the ZX diagram inside the black box, inside the small black box, which is the local gadget, right? And then you use ZX rules to bring the ZX diagram, whatever, inside this black box into this following form. So it can have some messy local things that inside the box, but most importantly, it has 3 stages. Right, the first stage is a spatial encoder, which enlarges the Hilbert space from the incoming and outgoing legs to a few local degrees of freedom, and then these local degrees of freedom are connected to neighboring gadgets because these are the bonds, right? These are the legs on the bonds, and then it goes through a dual encoder so that it goes back to the number of physical qubits that were at the place. So. And the next step is to further use the ZX rules to actually merge the dual encoder and the encoder in the middle of the circuit, so that it becomes a internal circuit that basically measures all the stabilizers of this encoder. So in the end, what you have is basically a circuit layout of these gadgets, right? Because before they are abstract tensors in ZX diagrams, and now after these steps, you can bring them into the actual circuit that can be implemented on quantum hardware. So this looks a little bit messy, so let's give an example of how this is achieved. And the example is actually the famous Hastings and Haah code. So let me just jump it over at first. The Hastings and Haah codes are built upon a toric code syndrome attraction circuit. So suppose we just start from toric code, right? So let's define toric code as a code on the square lattice. This is actually the rotated toric code. This is a surface code layout where each shaded square hosts a product of 4x, the stabilizers, and each unshaded, each white square hosts a product of 4z stabilizers. And so you want to say, okay, I want to construct a syndrome attraction circuit for toric code. And so following the steps that we laid out, what happens is, you first replace the qubits of the toric code by these gadgets that are locally that are put on locally, and that the connectivity actually follows from the connectivity of the square lattice. So this is how they're actually connected. And just a notation, the time actually goes in this direction. The time actually is going in the diagonal direction. So this is rather a 2D play on the 3D graph. So let's follow the intuition that we had, that the gadgets are local encoders, and they measure, the desired stabilizer and generate a set of new ones. So, for example, we can focus on this, 4-body X stabilizers, right? Focus on this 4-body X stabilizers. So they should be mapped to, these bond operators that connects, the 4 gadgets that are shaded here. Let's give these bond operators some names, right? Let's just put up an ansatz, and we will later solve for these operators. So we give the names A, B, C, and D with a subscript X to indicate that they're mapped from incoming X operator. And similarly, you can do this with the incoming Z operators, which is done over here, right? So what happens is the incoming wait for Z operators are mapped to these bonds, and we also give the bond operators names A, B, C, and D with subscript Z. And we demand translation invariance. So every X and every Z operator, so every X and Z stabilizers are mapped to the same set of bond operators, right? So so with that, then we focus locally on one single gadget, right, which is what happened on the left. We focus on one single gadget, and we track, how the gadget maps, the poly operators to the bonds, right? So for example, the gadget on the bottom left, we see that, okay, because there is an X stabilizers to the bottom right of this gadget, what happens is, it needs to map X to the legs that we label by 3 and 4, right? So X is mapped to C and D, right? And similarly, since there is another X stabilizers on the top left of the gadget, it has to map to these two legs on the top left, which is we mark as A and B, right? So in total, each gadget is involved in 8 stabilizers, 4 incoming stabilizers, and 4 outgoing stabilizers. So it should at least perform these maps. Sorry, question?
Yes, I wonder, you said translation invariant. Why this is an important restrictions when you're doing the mapping?
No, it's just for the for convenience, right? Obviously, you can like it can be different for every gadget inside this code, but since the Tori code is translation invariant, and so the simplest ansatz you can set up is that all the boundary operators are the same, like they're translation invariant.
Okay, thank you.
Yeah. So I mean, obviously you can do it differently, but yeah, it's just for the sake of easiness. Okay, so now you set up these 8 maps that the gadget needs to perform, right? All of them form all of them are basically part of the encoding maps of the gadget, because we mentioned that the gadget is a local encoder. Okay, so what happens next is you have to determine A, B, C, and D, right? So we come up with these set of commutation rules that A, B, C, and D need to satisfy, because they're encoders of incoming and outgoing poly operators. So for example, if we focus on these 2 graphs, right, these 2 encoding maps, you find that you have an encoding map of X and encoding map of Z. Since X anti-commutes with Z, their maps has to anti-commute, right? But we know that the maps are essentially only overlapped on leg 3, right? So which means that CX has to anti-commute with CZ, right? Because X anti-commutes with Z, and C and D for X and B and C for Z are the maps, are the encoded logical X and logical Z, right? So which means that whenever they overlap, they have to anti-commute, right? So that this is what happens. And similarly, you can focus on these 2 graphs, and you can convince yourself that AX has to anti-commute with AZ, right? And so you collect all these commutation rules that need to satisfy for these operators A, B, C, D, and you come up with these set of rules on the right, right? These set of rules that A, B, C, D needs to satisfy on the right. So so what we found is that there's actually a very simple solution for these operators. So the operators can all equal to each other, A, B, C, and D. The solution is here. So the solution is that A, B, C, D all equal to a single poly operator. Actually, one single poly operator is enough. So what we found is, they can just equal to poly operators P and Q, and P, Q are basically either X, Y, or Z. And you can just choose, P not equal to Q, and they're both poly operators. And this is going to satisfy, all the constraints.
So the solution, maybe I want to add something. The solutions you have found are such that there is consistency across the bonds that connect the gadgets. For example, you have these white gadgets and the orange gadgets, and if they're connected with a bond, then the maps are consistent on that bond, right? Maybe you.
Yeah, let me actually go back. So because if you draw the square lattice in this way, like if you draw the rotated Tori code, actually that you have 2 types of sublattices, right? So you have 2 types of gadgets essentially. Like you have the L1, the R1, right? And the L1, R1 are kind of rotated by 90 degrees, right? Because the local environment is different, right? The L gadget has X stabilizers on the bottom right and top left, and the right gadget has the X stabilizers on top right and bottom left. So yeah, but so you have to actually remake a set of equations for the R gadget, but since they're interconnected, you kind of already know what these equations are, and so that means once you figure out the L gadget, the R gadget is kind of just very straightforward. Okay, so let's actually continue, and so we choose we choose a P and Q equal to X and Y, right? If we choose P and Q equal to X and Y, what we found is that the gadget is actually, stabilized by these encoding maps. So it maps, incoming X to P on the two legs, right? We label the 4 internal legs by 1, 2, 3, and 4. So this is what happens, right? The X is mapped to P at 1 and 2, or P at 3 and 4, etc. So in total, you have these 8 rows. Each row is, one of the encoding maps here. And if we pick, P equal to X and Q equal to Y, then we run this, ZX diagrammatic algorithm by Andrew Kessing and collaborators. And what we found is that, the ZX diagram looks like this, right? It looks like a hexagon, with the 6 legs sticking out being the incoming and outgoing, and 1, 2, 3, 4. And for the sake of convenience, we actually introduce another new tensor, which is a Y tensor. The Y tensor is basically X tensor conjugated by 3 phase gates. So that is stabilized by all the Y's that are supported on the 3 legs. So once this gadget is repeated over time, what happens is, is we have the ZX diagram on the bottom left, right? We have the ZX diagram on the bottom left, and this is actually already in a 3-stage form, if you can see this. So the easy way to see is we draw, we kind of can decompose the diagram into this part, right? This part and this part, right? So this part is a spatial encoder of basically a 2-qubit repetition code, right? And similarly for the third stage. And the second stage is basically inter-gadget dynamics. So once the gadget is repeated, what happens is, you can actually merge the thing in the middle, right? You're actually merging the spatial encoder and dual spatial encoder. So after merging them, what happens is they become this, right? They become a pairwise measurement in Z inside the gadget, right? And furthermore, you have these legs that are sticking out. These are X tensors and Y tensors. What happens, they are going to be connected to other X and Y tensors at nearby gadgets, right? So suppose you have another gadget that's somewhere here, so it will actually be connected, right? So whenever these 2 gadgets are connected, you perform a pairwise measurement in X, right? So just to illustrate how, after connecting these gadgets, what the circuit will look like, we have this. Wait a sec. So this is what happened, right? So let's write this circuit in a very compact fashion, right? So we replace, we kind of denote the 2 lines, which are now 2 physical qubits, right? The timeline of the 2 physical qubits. We put these 2 physical qubits here. We mark them in black, and the X and Y legs are colored by blue and red. So this is basically a gadget, like the physical layout of the gadget. And then what we do is we replace all these gadgets. Remember this diagram here, right? We replace all these black boxes by what actually is inside the box, right? So what happens is we would put them here on the square lattice and try to connect all these legs. And what we found is that once these blue legs are connected, right? Once these blue legs are connected, since the blue leg originates from an X tensor, what happens, once you connect them, they will actually become, a pairwise measurement of X times X. And similarly, if you connect all these red legs here, here, and here, etc., so what happens is, that this becomes a pairwise measurement of Z times Z, right? And remember that the green leg is actually a pairwise measurement of Z, not Z, Y and Y. And inside the gadget, this one is a pairwise measurement of Z and Z. So indeed, we recover actually the Hastings and Haah flocate code, which is on a different lattice layout. This is a square octagon lattice, right? So yeah, this is basically a first application of spacetime concatenation. It produces the Hastings and Haah flocate code, and building upon this simple example, what we do is, we're trying to generalize this construction to a novel LDPC code that's, widely studied in some literature, which is the bivariate bicycle code. So the bivariate bicycle code can be thought of as, a generalization of Tor code, with some long range connections in its checks. So basically what happens is, you have these data qubits, which are the circles on this diagram. And the checks are marked in boxes like the pink and green boxes. So each check involves, for example, you focus on this check over here. It actually involves 6 qubits. So it has, connections to 4 neighboring qubits and 2 very far qubits, right? So each check involves 6 qubits. You can say 4 local and 2 far away. And similarly for the Z check, it also involves in 6 qubits, 4 local and 2 far away. So let's say we want to deploy the gadget decomposition and construct a dynamical code on top of the bivariate bicycle code. What happens is, we actually find that, we need to first of all replace these physical qubits, these L and R data qubits, by a gadget. And the gadgets are interconnected according to this, tanagraph of the BB code. And what we found is that, actually, each L and R gadgets needs to be connected to, 9 other gadgets that surrounds it, because, there are 9 lattice directions instead of 4. There are actually, three ways a cycle can go along this tanagraph. So, so this 9 connection that we have means that, that there is a new set of bond operator that we need to specify for all these 9 directions, right? So, so what happens is, so we can still think of a picture of that we started with Tor code, right? That the incoming poly operators are mapped onto these bonds. But now for the BB code, what happened is, every incoming X, for example, for the L gadget, is mapped to these 9 directions that share the same first index. So it maps to, sorry, it maps to this, or it maps to this, or it maps to this. Like, this is a matrix that basically writes down the 9 directions, or the 9 entries of this this matrix. And what we found is that, some of the entries needs to be weight 2 in order to, reproduce, the poly algebra on the incoming and outgoing legs. And yeah, so there's
and that's the reason that you had 2 legs on some of the bonds in the picture.
Yeah, so yeah, exactly. So that's why there are 2 legs, on some of the directions on this, like the diagonal directions 1, 1, 2, 2, and 3, 3. So after after finding out these encoding maps, we can again construct a ZX diagram encoder of this local gadget. And what we found is that the diagram looks like this. This is basically the one that reproduces the encoding maps here, according to these encoding maps. And if you do some massaging of the ZX diagram on the left, which is rather messy, what you found is some nicer looking ZX diagram. And you can deploy ZX rules and bring it into a circuit layout. And from the circuit layout, you can now repeat it, and you can basically get the Fouquet version of the BB code, where actually here we did a little trick, because the encoding map is actually not CSS. The outgoing leg has a Hadamard box inside. So if we just repeat the gadget by flipping the time order, which people sometimes call rewinding, these 2 Hadamard boxes, they cancel out, and we have something nicer that's purely measurements. There's no unitaries here. So what happens is we found that two repetitions of this dynamical BB code can be brought into this form. This is a 14 round schedule that involves measurement. So for example, this is So for step 0, what we have is pairwise measurement of Z inside the gadget. At step 1, we have inter-gadget XX measurement, and at step 2, we have intra-gadget weight 3 Z measurements, and etc. So yeah, this is basically how we can construct an example that we can construct Fouquet codes for more general LDPC code. Okay, so for the rest of the talk, so are there any questions? Okay.
Can you say again what the double edges correspond to in the ZX picture?
Oh, the double edges are basically, there are 2 legs going that direction. There are 2 legs going that direction, and if you from the ZX diagram, you can see that there are 2 legs too. Like there's like 1 1, there's 1 1 prime, there's 2 2, there's 2 2 prime. The prime just means that it's another leg that goes in the direction of 2 and 2.
But what is it connecting? Sorry, I'm not following.
Yeah, it's connecting the gadgets, right? It's connecting L gadgets with the R gadget, right? It's connecting on this diagram. So these are the internal legs. So each of the L gadget has essentially 12 internal legs, right, in 9 directions, right? The 9 directions are labeled from 1 1 to 3 3. And along the directions of 1 1 2 2 and 3 3, there are actually 2 legs. So in total, there are 12 legs.
Oh, okay, I see. Yeah, so each edge is it's the vertical direction corresponding to the stabilizer.
Yeah. Yeah, so there isn't really a nice kind of lattice layout of the entire protocol, so we didn't intend to bring that up, but implicitly you know what the circuit actually is, because locally we already bring it into a circuit form. Okay, so all right, so if there's no further questions, I will let Arpit take away.
Hello, can I ask a question?
Yeah, sure.
The very last slide you had, apologies, I don't know if I missed this, but the 1 1 2 2 and 3 3 spatially in the lattice, where is 3 3 located?
Oh yeah, good question actually. 3 3 is the long range one, right? So if you look at this, this is not exactly 3 3. So 3 3 will essentially be the connection between. Yeah, if you zoom in, the 3 3 is actually the connection between. 3 3 is actually the connection between these 2 guys, because they share an X and Z stabilizer, right? So they have to be connected as gadgets, right? So this will be kind of a 3 3 direction. And yeah, so because the code is not like graphically, it's not perfectly local 2D, right? The connections are not like the inter-gadget connections will be overlapping with each other if you draw everything on a 2D plane. So that's why it actually goes like. Sorry, question?
Oh, I have a follow-up. Because in your ZX diagram, the 1 1 2 2 and 3 3 are all symmetric. In the diagram, does this mean that this lattice picture is not capturing the symmetry of the 3 3 direction relative to the other 2?
Oh yeah, like this is just one way to put down, like you have to compromise, right? Like, because there are 3 directions, there are actually 3 cycles running around, but like you're putting things on the torus. There's no such thing as a 3rd direction, right? So the 3rd direction is rather non-local.
I see. Thank you very much.
Yeah, so you can choose different ways, right? Like for example, this is just one way to say, okay, I put 1s and 2s, right, as nearest neighbors, then 3 is long range. But everything involves 3 is long range, right? Question?
So the BP code is like 2-planar, right? We can put them on 2 planes and have connection. Is it obvious that the flow-catified version is also 2-planar?
Good question. I need to think about that, because we know that the Tanner graph is kind of 2-planar, right? For the BB code, right? Like it can be decomposed into 2 subgraphs. Each of the graph is planar. But the connectivity graph of the gadgets is not exactly a tandem graph because there's no checks, right? Like it's just the data qubits, the connectivity. So I would guess there is a similar level of locality on the graph if you decompose that, but I don't have a very straightforward way to connect all to think about how to decompose the connectivity graph for gadgets. But I would imagine there's a similar level of two planarness maybe inside the connectivity. Okay. Yeah. Oops, sorry, question?
Maybe one more question. So what kind of codes does this construction apply to? Do they need to be local or does it work for arbitrary stabilizer codes?
Yeah, so there needs to be some sense of locality. Like, I mean, at the bottom level, you can just say, okay, if every qubit is itself, right? That's some sense of locality, and you obviously, you have a geometric or graph sense of locality, like for example k locality. That is what we want, because if you have that, then you can start talking about codistance, space-time codistance, because due to the localities. And I think Arpit is going to cover that, like how the sense of locality influences space-time codistance of the entire dynamical. Sorry, Sarah.
Yeah, thank you for the talk. I wonder.
No, so sorry, we haven't finished. Like
I just, since you're here. So
okay.
This looks very similar to the definition of hypergraph product codes. Is it possible to generalize your methods for that code as well?
Oh yeah, absolutely. Like hypergraph product code is like, I mean, probably a simpler case than BB code, right? BB code is a lifted product code, like it's a generalization of hypergraph product code. So definitely, yeah.
Yeah, so the method applies to arbitrary LDPC stabilizer codes. Yeah. So, and we think it could also generalize pretty easily to non-LDPC codes, but we don't discuss that for this talk.
And intuitively, what would be the challenge, at least with the method at hand for non-LDPC?
It's mostly about preserving the algebra in a way, like if you are, so I think I will discuss that to some extent, like how these operators map, and so maybe I can go ahead with that.
Okay.
Yeah, so do you see my slides?
Yes.
Okay, great. So Yichen explained how he constructs the maps of these gadgets onto the actions of those gadgets onto these incoming poly operators. For example, for the toric code, for the Hastings-Haah K code, which is for the toric code, he found these gadget maps onto the incoming poly operators. So X maps to, for example, XX onto these bonds. And these maps are found in a way such that if you try to combine these maps for incoming poly operators and use them to look at the map for a stabilizer, like this XXXX stabilizer shown on the right, then they consistently map onto these four bonds onto which they map in a way that, each of those maps are consistent onto the pairs of bonds they map. So for example, X here would map onto X and X on these two bonds, and X over here will also map to X and X on these bonds so that they are consistent on this vertical bond. Do you see my mouse cursor, by the way? Yeah. Okay, so let me just remove this.
May I ask a very quick question about that?
Yeah.
How is this related to Pauli webs, or is this just Pauli webs, or is there a difference?
It's just web, yeah.
Yeah, so the webs we will talk about are the webs of these stabilizers. And so if you take an incoming stabilizer like this X stabilizer, right? So the poly web for this incoming X stabilizer will close inside the gadget, meaning that, these maps for each of these poly X's will kind of overlap on these bonds. and you can algebraically think of them as canceling on those bonds. And that's kind of the physical that's the reason for like physically measuring these stabilizers. That's like the mathematical uh, representation of how these stabilizers get measured inside the space-time dynamics specified by the gadget. So, so there are two concepts that we have used in constructing these gadget maps. One is strict locality preservation, which basically says that the gadget should maps onto these bonds, and these bonds are specified. Gadgets should map onto the bonds, uh, map the incoming poly operators onto the bonds that are coming out of the gadget. So for example, here we are showing these gadgets where four bonds are coming out of the gadgets in the plane. So the maps of these incoming poly operators should be onto onto a subset of those bonds. And these bonds are chosen according to the connectivity of the Tanner graph, like the connectivity that we have for some minimum weight stabilizer generator basis that's used in the Tanner graph. And so in that sense, there is a locality preservation that this gadget has because it tries to map these incoming poly operators onto certain bonds that are connecting the gadgets. It's not like arbitrary, bonds connecting gadgets far away. These gadgets are the connectivity between the gadgets is chosen according to that minimum weights stabilizer generator basis that shows up in the Tanner graph. So in that sense, there is this locality preservation that we have for these gadgets. And we have a technical algorithm in the paper which tells you that these bonds connect the qubits uh, that appear in a pair of incoming X and Z stabilizers together. So I would refer you to that algorithm in the paper to see exactly how this gadget layout is constructed. But the key idea is that we have this strict locality preservation. And the other point that I want to note, which I've mentioned, is that the stabilizers that are supported on these incoming legs or the outgoing legs, because that's where we have the incoming stabilizer code and the outgoing stabilizer code, these map onto the bond operators in a way that algebraically you can see that these maps of individual poly operators cancel out on those bonds. So here, when we look at these maps on the left-hand side, if you join four of such maps, such that you have the map of the incoming stabilizer, you will see that these poly operators, in an algebraic sense, you can think of them as canceling out. But is what actually happens is we care about the consistency of these neighboring gadgets. And algebraically, we can think of that as like some sort of cancellation. And so keeping this in mind, we can now think of condition for fault tolerance. So let me go to the next slide. Yeah, so I have two conditions for fault tolerance. One is called the bond kernel rank condition, and the other is what I have already alluded to, which is the strict locality preservation condition. So the first condition ensures that we do not measure any logical operators. So, as I said, for the stabilizers, the polyweb closes inside the space-time dynamics specified by the gadget. And that closing inside basically means that there is this algebraic cancellation of the maps of the poly operators that form the stabilizers, right? So, that cancellation can be expressed algebraically as in the form of a kernel of the rows that appear in the stabilizer tableau that Yichen showed for the toric code, for the Floquet toric code. So these rows in the stabilizer tableau specify the maps onto the bond operators. And so when these maps onto the bond operators cancel out for some incoming poly operators, that means you have measured those that poly operator inside the space-time dynamics of the gadget. And we want that to happen only for the incoming and outgoing stabilizers. We don't want that to happen for the logical operators. For the logical operators, we want them to flow through the gadget up to some logical automorphism, right? That's the non-trivial aspect of our construction, that we are able to reproduce non-trivial logical automorphism codes. And so we want the logical operators to go through our gadget up to some automorphism, but we want the stabilizers to be measured. So we write this sort of condition where we say that this HG, which HG transpose, which contains the rows of the stabilizer tableau that is specified for the gadget, meaning it just stores the maps of these different poly operators. This, if you take linear combination of those rows, it tells you what incoming poly operators map onto the bond operators in a way that their action on the bond operators cancel out. And so that's what this condition is showing. And we want to calculate the rank of such poly operators that cancel out under their maps onto the bond operators. And we want to say that that's just equal to the total number of incoming and outgoing stabilizers. And if that's true, that means you don't measure any logical operators. So that's our bond kernel rank condition, which we always check for any flow K code construction. And the second thing is the strict K locality preservation condition, which is used to argue that the space-time distance is not reduced across this dynamics. So, and this basically uses the fact that when we are using these gadget maps, when we are specifying these gadget maps with this locality constraint, then the evolved stabilizers under the space-time dynamics are also local, because are also as local as the locality constraint you specify on the gadgets map, right? So in that sense, because the algebra of the errors on the incoming stabilizers uh, sort of carries over to the space-time dynamics, right? So because of that, because of the preservation of that kind of algebra, it tells you that if all stabilizers are local, then the errors also do not spread out as you perform the space-time dynamics. And because of that reason, the space-time coordinate is bounded by the incoming stabilizer coordinate. So to see this very concretely, we specify the arguments very carefully in the paper, so I would refer you to that, but this is the core argument. And combining these two conditions, we know that we do not measure the logical operators. And if we don't measure the logical operators, then we care about preserving the space-time distance. And so we show that that's preserved if you provide a distance d for the incoming stabilizer code, the space-time distance is bounded by d. Even though we do some sort of concatenation and unconcatenation in the process of this constructing this dynamical code. Okay, so yeah, so that was about fault tolerance. Another property of our construction that I want to highlight is that it's a hardware first approach, in the sense that we could be given a layout of qubits in a real hardware, and some qubits might be lost, some connectors might be lost, and we can try to construct a gadget decomposition. We can try to write this gadget decomposition based on the qubits that we have in the real hardware layout. So in that sense, this provides a hardware first approach to think of what solutions of syndrome extraction compilation exist for a given hardware layout of qubits. If you're interested in, let's say, compiling a toric core syndrome extraction circuit, but some qubits are missing, some connectors are missing. So how do you compile the syndrome extraction? What's the best syndrome extraction in compilation in that case? And so you can write a gadget layout for that layout of qubits, gadget decomposition for that layout of qubits, and try to look for solutions of compilation. So in that sense, this is a hardware first approach. And I want to give you an example over here where a connector in our gadget layout is broken. So Yichen showed you that for the Hastings half-loc code, this is the solution for the gadget maps. Like this is the way the incoming poly operators map onto these bond operators for one kind of gadget, which is the white kind of gadget that was appearing because we had two sublattices of the gadgets. And the other one was automatically specified due to the consistency with this white gadget because it was neighboring to this white gadget. So, uh, yeah, so the question I'm interested in, what happens when a connector is broken? So now this vertical bond over here, like that is just broken. So we will not be able to uh, sort of connect these gadgets and use the solutions that we found above, right? So then the question is, what do you do in that case? How do you change the maps of these gadgets? How do you change the maps of these gadgets which have a broken bond next to them? And the way you change these maps is you can make them slightly non-local. For example, here, this bond is the one that is broken, right? This is the bond that is broken. And now this incoming x, we can say that if you map this incoming x in onto this xi, xy, and something far away, xy and xy over here, and this x also xi, xy, 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 then the stabilizer, this incoming stabilizer still cancels out on the bonds. And the algebra for these incoming x and the incoming z's over here, that is also preserved. And so this is another solution, but this is slightly non-local. And we need this sort of non-local solution because this bond is broken. And now if you try to, so you write the stabilizer tableau corresponding to this map, you use that stabilizer tableau to write the ZX diagram, and you will then join these ZX diagrams together for the neighboring gadgets in this form and come up with a circuit schedule with with pairwise measurements. And we find the 6-round schedule where you measure the ZZ bonds on the green legs, and then you do these XX measurements, and you do these single qubit XX measurements over here. And this is due to the fact that we have a broken connector over here. So we get a 6-round schedule. And this kind of insight also applies when you try to construct boundary, because you can imagine a boundary as just a whole line of broken connectors. So over here, I have this gadget layout that we had for the Hastings half-loc code. I have rotated it right now such that these plaquettes made of these blue and uh, red edges, they look like this. They are just rotated from the previous picture that we had shown you. So now what you can do is you can just break these green bonds at the top, and that will lead to a lot of broken connectors. And then you can ask, what is the right schedule in this case? And one of the right schedules in this case is again a 6-round schedule, and it's a 6-round rewinding schedule, which kind of does this. It's like you first measure things on the blue bonds, then the green bonds, then red, and then blue, and then you go back to red and then green. And whenever you see a broken connector, that means you are also you're measuring half of that broken connector. So here, if you see a green bond, you measure just half of that. So that's a single qubit measurement. And so this is a sort of uh, 6-round rewinding schedule, and it comes out of this philosophy of broken connectors and trying to modify the schedule such that you satisfy both of our fault tolerance conditions. And so one of the fault tolerance conditions we had was this bond kernel rank condition. And I want to say that that's the one that requires a 6 round rewinding schedule if you want to satisfy that. If I try to use the 3 round schedule, I will see that on the boundary, I will be starting with these single qubit stabilizers. Let's say uh, I'm measuring, let's say the green bonds are made of these Y measurements. So in this picture, the basis is slightly changed, but so forgive me for that. But the point is that the green bonds are broken, and so you're doing these single qubit Y measurements. And as you go to the next round, to the blue round, then these single qubit Y measurements join together to form a slightly non-local stabilizer. And then you go to the R round where you measure the red bonds. These are the new stabilizers that are at the boundary. They are made of excess. And when you finally come back to the green round, these stabilizers join together to form a non-local stabilizer. And that actually leads to measurement of the logical. So in order to avoid that, in order to satisfy this bond kernel rank condition, which is not satisfied with this 3 round schedule, we use that rewinding 6 round schedule. So this is a way in which our fault tolerance conditions show up when we try to deal with fabrication defects and boundaries, domains, all kinds of things. But in some sense, our approach is very general and is able to sort of capture these different kinds of scenarios. So just to summarize, I want to say that our approach is a hardware first approach for compiling syndrome extraction and choosing between different forms of syndrome extraction. And one non-trivial property that we mentioned is previous general recipes for coming up with Floquet codes worked for trivial automorphisms, trivial logical gate transformations during the syndrome extraction process, right? But our approach is able to work and output solutions that have non-trivial logical automorphisms, meaning that they perform non-trivial logical gates as you are doing syndrome extraction. So in that sense, you can try to look for more codes with interesting non-trivial logical automorphism as you perform syndrome extraction and come up with a family of these so-called dynamical automorphism codes where you try to do several gates during the syndrome extraction process. Uh, Lastly, the work that we presented today was for poly stabilizer codes. And so these poly stabilizer codes described abelian topological order. And one question that we are currently interested in is generalizing our framework to non-abelian topological orders. So in the sense, we can construct non-abelian Floquet codes and maybe even generalizations of such non-abelian codes to LDPC codes. So with that, I would like to thank you for your attention.
Let's thank our speakers for the fantastic talk. You can do a clap emoji. Clap on the screen. Yeah. And I suppose the floor is open to any questions.
I think you can just ask, sorry.
Yeah. Hey, thanks a lot for the nice talk. So I had a question about this argument of like fault tolerance, which I didn't fully understand. So maybe the first question is, so you're saying the space-time distance of your circuit is lower bounded by the distance of the code, right?
Yeah.
How can it ever be larger than the distance of your code? Because at the very least, if you just have Pauli flips at the very end of your thing, so it would be the same, right?
So great question. So I think there is some subtlety that wasn't fully expressed in that proof slide, is that we are doing a concatenation for this incoming stabilizer code. So let's say you have a 4-qubit code or toric code on n qubits, and then we do a 2-qubit repetition code concatenation for each of the physical qubits of the toric code. So that concatenation is part of our framework. So in that sense, and actually it's the concatenated version that is physical. Like that's the number of physical qubits we use in the actual dynamics. So this sort of concatenation and unconcatenation is not really something at the physical level. That's more at the algebraic level, at this framework level. But in an actual physical setting, what you will do is this concatenation will already be part of the description of the code, and you would be performing your dynamics on this concatenated level set of qubits. So I guess we are comparing the code distance, the space-time code distance, to the code distance of this unconcatenated incoming toric code. So in that sense, there is the greater than equal to over there. But yeah. So it's more like, yeah, if you try to add this concatenation on the toric code, right? And if you let's say look at the distance associated with one kind of logical, then that might look a little bigger than this incoming code distance. Like, you know, depending on the kind of concatenation you do, it might look bigger.
Yeah, so yeah, just add a little bit. So this is the general like format of the space-time concatenation, right? So you see like these two legs, horizontal direction, they are like physical qubits before concatenation. Like that's the data qubits of a stabilizer code. But when it enters the ZX diagram, it first goes through the spatial encoder, so it becomes more, right? So for example, there are 6 lines here. These are actually 6 physical qubits, right, that we're actually operating on. So after the spatial encoder, actually, we're doing this conventional code concatenation, right? So the started arrow, right? This is the place where you already switch from a unconcatenated to concatenated. That's conventional concatenation, and actually we never do this conventional concatenation because in the actual circular implementation we merge the spatial encoder and the dual encoder so that it becomes a bunch of measurements, right? So we always operate inside the concatenated code space. Right, so that's why that the space-time code distance is at least, right? We say at least because that's the origin of this inequality.
And how can you ignore the propagation? And you can ignore the propagation of errors through the circuit because of the locality constraint, where like because even if my errors propagate, they stay sufficiently local, and therefore like I can already make this argument that is that correct?
Yeah. So
I see. Okay.
yeah, you can think of it as the stabilizers. Yeah, if you want to think of it at the like, how do the logicals look like? Your stabilizers are evolving, and maybe they are becoming, in some cases, you could imagine they might become non-local. And so you might be interested in how the logical for this instantaneous stabilizer group looks like. And if the stabilizers remain as local as your initial set of stabilizers, then the logical does not the code distance doesn't change for these instantaneous stabilizer groups that you encounter. If the stabilizers evolve into some non-local stabilizers, then the logical change in their spread, and so the code distance can change. So if you want to think in terms of the instantaneous stabilizer groups, that's another way to think about it.
Right. I think for that I understand it more. For the circuit perspective, I struggle a little bit with the propagation of the faults throughout the circuit, but I guess measurements don't propagate them. Well, kind of depends on how you view it, I guess.
Yeah,
okay,
so
I think in terms
that
of
the
ISGs,
propagation can be dealt with, like, you can either, like, it's a Heisenberg versus Schrodinger picture, right? I guess that's what, right? Like, you can deploy the Heisenberg picture and say, okay, they're all, like, the errors are propagating. We can also say that the Schrodinger picture is we just have a circuit, right? And if it occurs in some space-time location, then it will touch some space-time. Like, the space-time detector kind of also spreads, right? Like, it's in the active picture, right? So you can use either picture and convince yourself that they don't spread, like if you have locality preservation. Yeah.
Okay, thank you.
Yeah, also there is this picture that we don't distinguish so much between circuits with unitary gates and measurements. Like you can think of every time instant, you have a evolved stabilizer group. And you can, because that's what also happens in the conventional syndrome extraction circuit, you're doing these C0 gates and your stabilizers are evolving. So at every time instant, you have an instantaneous stabilizer group. And you can try to think in terms of those instantaneous stabilizer groups for a circuit that consists of unitary gates or measurements. It doesn't matter.
Yeah, but for example, sorry, I'm
Confused
taking up a lot
about
of.
this. Oh, sorry. I'm a bit confused about this.
Yeah.
Oh,
No, go ahead.
I'm a bit confused about this concatenation. Where is this concatenation coming from? Like, how do you know what you're concatenating?
Okay, that's actually a good question because, if you look at our kind of workflow right on this slide, you already know what's inside the black box, presumably, like using the algorithm, like the diagrammatic algorithm to construct the X diagram of an encoder. But you actually have, different ways to bring it into a three-stage form. Like you can always bring it to three-stage form because, it's like, playing with noodles. You can form it in different shapes. But there are different ways that you can bring it to a three-stage form, and each different ways means that there are actually different number of physical qubits, and you're choosing a different spatial encoder, right? So you have the freedom to actually play with what spatial encoders that you want to use, right? For example, we say, okay, for toric code, this is the ZX diagram, right? This is a hexagonal one. But actually, there's another way to draw this ZX diagram in which, you have 4 physical qubits instead of 2. So if you draw it this way, it looks like you have 2 physical qubits undergo some dynamics. And you can also choose 4 physical qubits. And for the case of BB code, we showed that there's a 6-qubit spatial concatenation. In our paper, there's a 12-qubit spatial concatenation. So there's a flexibility of playing with the ZX diagram in this workflow. So it's actually not fixed, and that's the beauty of Spacetime concatenation, because you have a flexibility of trading different computation resources, like whether maybe you have more physical qubits to play with, or maybe your coherence time is long, so you can tolerate deeper circuit. You can trade space with time in this formalism, right?
Yeah, that's cool.
But the spatial encoder always encodes one logical qubit, right? Or can it actually encode multiple?
It can actually
always
encode
one physical.
So I intentionally not draw one in time. Like I drew 2 because you can also always like coarse grain, right? You can always coarse grain the stabilizer code, right? So you have a coarser sense of locality, right? Actually, that's one of the examples that we did in our paper. We studied the Haah's qubit code. That's the case where in Haah's qubit code you are on a cubic lattice, but on each lattice side there are 2 qubits, right? So you can just say, okay, directly that the 2 lines goes into one single gadget. That's possible. So now the gadget actually has 2 times 2 logicals instead of 1 times 2, right? But also you can say, okay, I can just use 1 gadget per physical qubit, and it will come with a finer sense of space-time concatenation. So yeah, that's also a degree of freedom you can play with. Yeah, so this is not very strict. This is also very flexible.
Another degree of freedom, not sure if you've thought about this or wondering what you think about this. Why does the dual of my encoder, why does that have to be the same code? Could I decode into another code?
Yeah.
And then as long as I encode into that code again, that's also fine. Is that something you've explored, or?
Yeah, I think that's always possible. Like, there's a very simple intuition of if you have an encoder and it's dual, they're directly connected, so you can directly merge them and it will be the syndrome extraction circuit, right? But you can also say, okay, the dual spatial encoder is not the same as the spatial encoder of that. Then it's not exactly the syndrome extraction circuit, but it's kind of a subsystem code between you change from one gauge to the other, right? So actually, in some of the examples, I think when we prove that we gave an example of Fouquet checkerboard code, and we're trying to prove the equivalence of that code with the existing Fouquet checkerboard code. In that case, the dual encoder is actually not equal to the encoder, and that's why merging them will yield like weight 3 intra-gadget measurements, whatever. So that is actually a case, and it's actually already presenting the paper. It's just like we didn't say it explicitly. Yeah.
So in this picture, is it possible to think of the vertical lines, like if I can reinterpret them as my data qubits and then my encoder and its dagger? Like, is that what you meant by trading space and time here? That my the two logical qubits going from left to right can be the bonds. Is it possible to just rotate it like this? Or
No. What I'm saying is, you have the fixed number of bonds going between gadgets, right? You have a fixed number, like for example, in this case, you have 10, right? You have 10 bond bags that are sticking out in the from the gadget, right? So you have to distribute 10, right? You can do a simple math that 10 is equal to maybe 2 times 5 is equal to 1 times 10. So you say, okay, if my spatial encoder is an encoder that has 10 physical qubits, then maybe you can do the inter-gadget dynamics in one single step, right? But maybe I have 5, maybe I have 6, and I have to do like multiple steps. Like for example, here, this is definitely not something very, very clean, but I say, okay, I can group everything in 3 steps. But roughly speaking, the product of the circuit depth times the number of physical qubits inside the gadget, right? This product is roughly fixed, right? It's the single quantity that's the number of internal legs of this gadget.
I see.
Right? That's what I mean by trading space with time, because space times time is kind of a upper bound. Like there is a quantifier of what space times time needs to equal to, right?
Sorry, so when you say you're trading space with time overhead, the top and bottom edges are the qubit count, so would be your space overhead. Is that correct?
Right. So the number of horizontal lines inside the gadget is the number of physical qubits, right? Like look at this dotted arrow, right? So the horizontal lines are basically the timelines of a physical qubit. Right. The horizontal lines are timelines of physical qubits. And the horizontal lines are basically the inter-gadget connections. Right. They're connected to nearby gadgets, right? So that number is fixed, right? That number is independent of what spatial encoder you choose. But if you choose it differently, you have a different space-time kind of layout.
Thank you.
There's another question by Benjamin. Sorry.
Yeah, I'll wait if anyone else has questions first. Otherwise, I'll go again. Okay, so this idea of, okay, edge end of the encoder followed by the encoder, that's just basically measuring one round of my stabilizers, right? But those might potentially, depending on my choice of spatial encoder, might be relatively high weight, right? And I think part of the idea of some of these flock codification procedures, at least, is kind of to break down high weight measurements into low weight measurements. So how do you take care of those internal measurements?
Yeah, that's a legit question. And to that, I think, unfortunately, you still have to deploy, some of these flockatification or like this dynamical weight reduction techniques in order to deal with internal measurements. Right? That's one straightforward way, right? Like if you still have high weight measurements inside the gadget. But I would argue that, since, we have a sense of locality, right? So these potential high weight measurements will all occur inside this very local region, right? So you can either deploy, dynamic weight reduction or flockatification inside this region, or you can, play with ZX calculus and find a combination of dual and spatial encoders. Like find a combination of them, which is not necessarily the same code. They can be different. They actually has to be different in order for some magic to happen, right? In order to this merged circuit to actually be lower weight measurements, right? So there's a clever way, there's a straightforward way, and I think both works.
And that not being fault-tolerantly done is kind of fine within this context, or?
Yeah, you actually need to do it in a quote-unquote like space-time distance preserving way, right? If you do it like carelessly, then maybe like you're just the space-time distance is only take the equal sign, right? But if you do it cleverly, then you take the large sign, right? When you're comparing space-time distance with the original stabilizer co-distance.
Yeah, I see. Thanks.